Alright, so I was talking about how we're going to use tangent lines to approximate actual function values. And I was at this point where I was getting ready to plug in 2. When I plug into 2 into this right here, I get 6/4, which is 3/2, which is 1.5. And when I plug into here, I get negative 12/8, which is, or not negative 12/8. I need to plug that into the tangent line to the curve, not into the function. So I want to plug 2 in for here. I get negative 3/2 times 2 plus 9/2. Those cancel, so I have negative 3 plus 4 1/2, which is 1.5 as well, which is what I should get because these two, the function and the tangent line, share that common point. So I should be getting the same values there. As I look to the right of this, something very, very close to 2. Remember, what we're trying to do is use a tangent line to approximate the actual height of the function. And so when I plug in 2.01 into, first of all, this function up here, I get 6 divided by 2.01 times 2.01. That equals 1.4851. And then I will take that same 2.01 and plug it in for the tangent line to the curve. So in this problem then I would get 1.5, a negative 1.5 times 2.01 equals this plus 4.5, which gives me 1.485. Notice how these are very, very close. And that's what you can see in the graph, that there's very little difference between the tangent line and the function value. You'll do that one more time for 2.1, and of course there would be a greater gap between these two because we're getting further away. So the further away we get from that point, the greater our difference between the actual function value and that tangent line is. That's what we're doing when we're using differentials. A differential is a dy over dx. We've seen dy over dx's in our derivatives. dy over dx equals f prime of x. I could solve for dy over dx, or for dy, by multiplying by dx on both sides. I do want to go ahead and show you that. So we're going to denote dy is equal to f prime of x dx. What you saw in that last example was how I was using tangent lines to approximate the actual function height. The actual change in y, okay, the distance between these 2 points, the y distance between them, we'll call change in y, is very, very close to what that height value is of that tangent line to the curve. Remember, it was really, really close the closer and closer we got to that point of 2, and it was not as, it was getting further and further apart as the further and further away we get from that point. What I want you guys to take note of is that we're going to decide or make note that the change in y is approximately equal to dy. It's not equal to dy. We saw how these were not equal to each other, but they're close to each other. So the last comment I want to make from this is that dy, since it's approximately the change in y, it would be approximately equal to, so the change in y is approximately equal to f prime of x dx. I'll continue with some other examples in the next video.